What if something from beyond our solar system isn't just passing through, but arriving, not drifting, not tumbling on some random path shaped by billions of years of cosmic chaos, but moving toward Jupiter with a level of precision that, according to the laws of probability, shouldn't happen by accident? The kind of precision that makes scientists stop talking, lean forward in their chairs, and whisper a question nobody wants to ask out loud. What if this isn't natural? This isn't about objects floating past planets. This is about something threading a needle across billions of kilometers, hitting a target so specific that even calling it luck feels like ignoring what the data is screaming at us. Stay with me for the next several minutes, because what we're about to examine isn't speculation dressed up as science. We're going to walk through real data from NASA's Jet Propulsion Laboratory, calculations verified by observatories around the world, and measurements that have divided the scientific community between those who prefer comfortable explanations and those willing to ask uncomfortable questions. We're going to look at an object called 3I Atlas, and specifically what it's doing right now, heading toward Jupiter's gravitational sphere of influence with a precision that defies the chaos we expect from random celestial mechanics. Here's what makes this situation extraordinary. Jupiter has what astronomers call a Hill radius, essentially a gravitational boundary, a sphere of influence where Jupiter's gravity dominates over the Sun's pull. For Jupiter, that boundary sits at a very specific distance from the planet's center. When scientists calculated where 3I Atlas would be on March 16, 2026, based on its current trajectory and the measured changes in its velocity, they discovered something unsettling. The object's minimum distance from Jupiter matches the Hill radius within margins so tight that the odds of it happening by chance are roughly 1 in 26,000. Think about that for a moment. This isn't sort of close or in the general neighborhood. This is threading a needle across billions of kilometers of space. Avi Loeb, the Harvard astrophysicist who has built a career on asking the questions other scientists avoid, looked at these numbers and didn't see coincidence. He saw a pattern that demanded explanation. When NASA held a briefing in November 2025 to present findings from 8 different space missions observing 3I Atlas, the tone was reassuring, almost dismissive. Yes, the object was interesting. Yes, it had some unusual characteristics, but fundamentally the message was clear. This is a comet. Nothing extraordinary. Move along. Loeb's response was swift and pointed. He accused the agency of minimizing the anomalies, of lowering expectations rather than raising the quality of investigation. His criticism wasn't based on conspiracy thinking or attention-seeking. It was rooted in the same data NASA was presenting, but viewed through a lens that refused to ignore uncomfortable implications. The tension here isn't just about one scientist disagreeing with an institution. It's about a fundamental divide in how we approach the unknown. On one side, there's the conservative position: assume natural explanations until absolutely forced to consider alternatives. On the other side, there's the position Loeb represents: investigate anomalies without preconceptions, follow the data wherever it leads, even if it leads somewhere that makes us uncomfortable. Both approaches have merit. Both have historical precedent. But when you're looking at an object that appears to be arriving at a gravitationally significant location, with precision that strains natural explanation, the question isn't which approach is more comfortable. The question is which approach is more honest. What makes March 2026 more than just another date on the calendar is that we're not talking about distant speculation. This is happening right now, unfolding in real time, and we have less than 2 years before the predicted arrival. If 3I Atlas reaches Jupiter's Hill radius exactly as calculated, we face a moment of scientific reckoning. Either we're witnessing a coincidence of staggering improbability, or we're witnessing something that requires us to expand our understanding of what's possible in our solar system. The comfortable answer is that comets can do strange things, that orbital mechanics are complex, that unusual outcomes sometimes emerge from natural processes. The uncomfortable answer is that precision suggests purpose, that mathematical exactitude at this scale might indicate intention rather than accident. The stakes go beyond academic debate. If an interstellar object is demonstrating controlled trajectory adjustment, if it's not just falling through space but navigating through space, then every assumption we hold about our cosmic isolation comes into question. We've spent decades searching for signals from distant civilizations, pointing radio telescopes at faraway stars, analyzing light from exoplanets for biosignatures. Meanwhile, according to the data Loeb is highlighting, something might be conducting a close-range investigation of the largest planet in our solar system, and doing so with the kind of precision that suggests advanced planning. The counter-argument is always available, always reasonable. Natural processes can mimic intentionality. Comets outgas unevenly as they warm, creating thrust that alters their paths. Gravitational interactions are complex and can produce surprising outcomes. The universe is vast enough and old enough that even unlikely events eventually occur. These points aren't wrong, they're just not sufficient to explain why this particular object, coming from interstellar space, would undergo course changes that place it at a gravitationally meaningful location with precision that exceeds what we'd expect from random processes. When you add up all the factors, the timing of the trajectory change, the location where it occurred, the exact magnitude needed to reach Jupiter's Hill radius, the natural explanation doesn't get stronger, it gets more strained. What Loeb is asking isn't unreasonable. He's asking for investigation that matches the scale of the anomaly. He's asking for systematic observation instead of opportunistic snapshots. He's asking for the kind of scientific attention we'd demand if we detected a radio signal from space that showed structured patterns. The response he's received has been mixed. Some researchers share his concern that we're not taking this seriously enough. Others dismiss his interpretation as premature, a leap toward extraordinary conclusions without exhausting ordinary possibilities. Both groups are working from the same data, seeing the same numbers, looking at the same trajectory plots. The difference is in what they're willing to consider. This is where you come in, not as passive audience, but as fellow investigators. Science isn't just something that happens in universities and government agencies. It happens when people pay attention, ask questions, demand rigor, and refuse to accept explanations that don't quite fit. The data about 3i Atlas is public. The calculations are available. The predictions are testable. March 2026 will arrive whether we're paying attention or not, and when it does, we'll see whether this object behaves as predicted. If it reaches Jupiter's Hill radius exactly as calculated, that's evidence that demands response. If it doesn't, that tells us something too. Either way, what we're witnessing right now is the unfolding of a natural experiment with implications that reach beyond astronomy into questions about our place in the universe. So here's what I'm asking. Share your perspective. Bring your skepticism, bring your theories, bring your calculations if you have them. This isn't about choosing sides between NASA and Loeb. It's about engaging with data that won't go away just because it makes us uncomfortable. Comment below with your thoughts on what's happening here. Not what you want to be true, but what you think the evidence actually suggests. Hit the like button if you believe this deserves more attention than it's getting, more investigation than it's receiving, and if you're someone who understands that the most important scientific moments often come when we're forced to question our assumptions, then subscribe and turn on notifications, because what happens in March 2026 might be one of those moments. We, the curious, need to keep watching this, keep questioning this, keep demanding that investigation match the scale of what we're seeing. The numbers are on the table, the calculations are verifiable, the prediction is testable. Now we wait, we watch, and we see whether the universe is about to show us something we weren't prepared to find. But waiting doesn't mean passive acceptance of whichever narrative feels most comfortable. It means active engagement with the possibility that we're witnessing something unprecedented, something that requires us to expand our thinking about what moves through our solar system and why. The assertion that 3i Atlas is heading toward Jupiter with impossible precision isn't hyperbole, it's mathematics. But to understand just how impossible this precision actually is, we need to look at the specific numbers that have scientists divided, the calculations that turned a curious observation into a controversy that won't disappear. When astronomers talk about Jupiter's Hill radius, they're describing something both simple and profound. A boundary in space where Jupiter's gravitational influence becomes stronger than the Sun's. It's not a physical barrier you could see or touch. It's a mathematical threshold, a sphere of dominance that extends outward from Jupiter in all directions. For an object approaching Jupiter, crossing into the Hill radius means entering territory where Jupiter, not the Sun, controls what happens next. The radius for Jupiter, given its massive size and distance from the Sun, sits at approximately 53.5 million kilometers from the planet's center. This isn't a round number chosen for convenience. It emerges from equations that balance gravitational forces, orbital mechanics, and the specific parameters of Jupiter's situation in the solar system. Now, here's where the situation with 3i Atlas becomes difficult to explain away with casual dismissals. Using data from the Jet Propulsion Laboratory's small body database, incorporating observations from more than 230 observatories worldwide, scientists calculated the predicted trajectory of 3i Atlas with the kind of precision modern astronomy has made routine. They factored in the object's velocity, its observed changes in acceleration, the gravitational influences from the Sun and planets, and every measurable variable that affects how objects move through space. The result of these calculations showed that on March 16, 2026, 3i Atlas would reach its closest approach to Jupiter at a distance of 3.445 million kilometers from the planet's center. Read those numbers again. Jupiter's Hill radius, 53.502 million kilometers. The predicted minimum distance for 3i Atlas, 53.445 million kilometers. The difference between these two values is less than 60,000 kilometers. In the context of interplanetary distances, this is nothing. It's not even a rounding error. It's precision that suggests targeting rather than coincidence. When you calculate the margin of error here, you're looking at a match within roughly 1 part in 1,000. But the full picture is actually more striking than that initial comparison suggests. When you account for the range of possible trajectories that a randomly moving interstellar object could take, when you factor in all the variables that could push it higher or lower relative to Jupiter's gravitational sphere, the probability of landing this close to the Hill radius by pure chance drops to approximately 1 in 26,000. Let that settle in your mind for a moment. Imagine throwing a dart at a target the size of the solar system and hitting a bullseye the width of Jupiter's gravitational boundary. Imagine doing it not from across a room but from across interstellar space, starting your throw from a point beyond the orbit of Neptune. Imagine that your dart somehow corrects its flight mid-journey, so that it arrives at exactly the location that matters most from a gravitational perspective. This is what the numbers are telling us happened with 3i Atlas. Either we're witnessing probability defying itself, or we're witnessing something that chose this destination with purpose. The trajectory data becomes even more interesting when you look at how 3i Atlas got to this precision. The object didn't simply fall toward Jupiter on a straight line. It underwent measurable acceleration that wasn't caused by gravity alone. This is documented in the JPL data, a clear indication of what astronomers call non-gravitational acceleration, meaning forces other than gravity were changing the object's velocity. For typical comets, this happens when ice on the surface heats up and vaporizes, creating jets of gas that push against the comet like tiny rocket engines. It's a well-understood natural process that explains why comets don't always follow purely gravitational paths. But here's what makes 3i Atlas different. The magnitude and timing of its acceleration were exactly what would be needed to shift its trajectory from wherever it was originally heading to a path that intersects Jupiter's Hill radius with the precision we're discussing. Think about what that means. If the non-gravitational acceleration had been slightly stronger or slightly weaker, 3i Atlas would miss the Hill radius by millions of kilometers. If the acceleration had occurred at a different point in the orbit, the effect on the final trajectory would have been completely different. But instead, the acceleration happened at the right time, with the right strength, in the right direction to produce an arrival at Jupiter's gravitational boundary that matches calculated predictions within margins that strain natural explanation. It's not just that the numbers align, it's that they align in multiple dimensions simultaneously: distance, timing, velocity, and direction, all converging on a single outcome that just happens to be the most gravitationally significant location relative to Jupiter. Loeb's analysis of this situation doesn't claim certainty. It claims that when you see this level of precision in natural systems, you demand extraordinary evidence for the natural explanation, not just comfortable assumptions. The standard response from more conservative astronomers is that comets are unpredictable, that outgassing can produce surprising results, that we don't fully understand all the factors influencing interstellar objects. All of this is true, but none of it explains why the unpredictability would resolve itself into such exact precision. If comets are chaotic and unpredictable, we'd expect their trajectories to scatter across a wide range of possible outcomes. We wouldn't expect them to converge on gravitationally meaningful targets with accuracy that suggests measurement and adjustment. The mathematics here aren't in dispute. NASA's own data confirms the trajectory. JPL's calculations are based on the same orbital mechanics that successfully guide spacecraft across the solar system with pinpoint accuracy. The observatories contributing data to this analysis represent some of the most sophisticated astronomical instruments humanity has built. When this much technical capability points toward the same conclusion about where an object is heading and when it will get there, dismissing the implications requires more than saying, "Comets do weird things." It requires explaining how this particular weird thing happened to produce results that look identical to what we'd expect from deliberate navigation. There's a concept in science called Bayesian reasoning, where you update your beliefs based on new evidence by comparing how likely that evidence would be under different hypotheses. Start with two possibilities. First, that 3I Atlas is a natural comet whose trajectory just happens to intersect Jupiter's Hill radius with extraordinary precision, or second, that 3I Atlas is something capable of controlled trajectory adjustment, deliberately targeting Jupiter's gravitational sphere. Now ask yourself which hypothesis makes the observed evidence more likely. Under the natural hypothesis, you need the object to undergo acceleration at exactly the right time, with exactly the right magnitude, producing exactly the outcome that matters most gravitationally. Under the technological hypothesis, you need an object capable of thrust control to fire its propulsion system during perihelion, when such maneuvers are most efficient, producing a trajectory that achieves a specific goal. Which scenario requires fewer improbable coincidences? This isn't about abandoning natural explanations. It's about demanding that natural explanations actually explain what we're seeing, rather than just waving toward general categories of phenomena. Yes, comets outgas. But do they outgas with precision that mimics intentional navigation? Yes, gravitational interactions are complex, but do they produce complexity that resolves into mathematical exactitude? Yes, unlikely events sometimes happen. But when an unlikely event happens to produce an outcome that looks purposeful, when it happens to an object coming from outside our solar system, when it happens to involve a gravitational boundary that would be significant for any mission trying to position something relative to Jupiter, the questions multiply faster than the answers. The prediction is testable. March 2026 isn't a vague future date lost in astronomical timescales. It's 16 months away as of now, close enough that mission planners are already preparing observation campaigns. If 3I Atlas reaches Jupiter's Hill radius as calculated, that's data that demands response. If it arrives even closer to the predicted value than current margins of error suggest, that's evidence that strengthens one interpretation considerably. And if somehow the object deviates significantly from the prediction, if it speeds up or slows down or changes direction in ways that move it away from the Hill radius, that tells us something crucial too. Either way, we're approaching a moment of verification where reality will confirm or reject what the mathematics are currently suggesting. The numbers don't care about our preferences. They don't care whether we're comfortable with implications or uncomfortable with possibilities. They simply describe what's happening with the precision that modern astronomy has earned through decades of refinement. 53.502 million kilometers, 53.445 million kilometers. These aren't approximate values dressed up to sound impressive. They're the output of careful measurement and rigorous calculation. And they're telling us that something is happening in our solar system that doesn't fit the patterns we've come to expect from objects that move through space without guidance, without intention, without purpose. What we're looking at isn't just one number that happens to match another number. We're looking at a cascade of factors: distance, timing, acceleration magnitude, trajectory adjustment, all converging on a single outcome that occupies a tiny slice of possibility space. When you roll dice enough times, you'll eventually get any specific combination you're looking for, but 3I Atlas didn't roll the dice millions of times. It rolled once, and it came up showing exactly the number that matters most from a gravitational perspective. That's not proof of anything by itself, but it's evidence that deserves investigation rather than dismissal, attention rather than minimization, questions rather than comfortable narratives. The scientific community is watching, some with skepticism, some with concern, some with the kind of cautious excitement that comes when you suspect you might be seeing something unprecedented, but aren't quite ready to say it out loud. The data will continue accumulating as observatories track the object's progress. The predictions will be refined as measurements improve, and in March 2026 we'll see whether this impossible alignment remains impossible all the way to its conclusion, or whether something happens that forces us to reconsider what we thought we understood about visitors from beyond our solar system. Understanding that the numbers align is one thing. Understanding how they came to align is another question entirely, and it's a question that leads directly to one of the most intriguing aspects of this whole situation. What happened during perihelion, when 3I Atlas passed closest to the Sun and disappeared behind it, hidden from our view for weeks while something changed its trajectory in ways we can measure but not fully explain. Perihelion is the point in any orbit where an object comes closest to the Sun. For comets, it's a moment of intense activity. Ice vaporizes under solar radiation, dust erupts from the surface. The whole object can undergo dramatic changes as it experiences the most extreme heating of its entire journey. For something travelling on a precise trajectory, perihelion represents something else entirely, an opportunity. If you wanted to adjust a course through the solar system, if you needed to make a maneuver that would determine where you end up months or years later, perihelion would be the optimal time to do it. The gravitational field is strongest there, meaning any propulsive thrust gets amplified by what's called the Loeb effect. Doing your burn deep in a gravity well multiplies the effectiveness of every bit of thrust you produce. It's basic orbital mechanics, the same principle that spacecraft engineers use when planning missions to the outer planets. For 3I Atlas, perihelion came at a time when the object was positioned on the opposite side of the Sun from Earth, meaning our telescopes couldn't observe it. There's nothing unusual about this. It's simple geometry. Objects pass behind the Sun regularly, and we lose track of them temporarily until they emerge on the other side. What makes the situation with 3I Atlas noteworthy is what happened during that observation gap. When the object reappeared and astronomers could measure its trajectory again, they found that its path had shifted. The measurements showed clear evidence of non-gravitational acceleration, meaning forces beyond just the Sun's gravity had acted on the object. This is where the data becomes impossible to ignore for anyone paying attention to details. The acceleration measured wasn't random. It wasn't the chaotic outgassing you might expect from a comet tumbling through space with ice, vaporizing unevenly from different parts of its surface. The magnitude of the change was exactly what would be needed to shift the minimum distance from Jupiter by the precise amount necessary to reach the Hill radius. Think about what this means. Before perihelion, based on the trajectory calculations, 3I Atlas was heading toward a closest approach to Jupiter that would have missed the Hill radius. After perihelion, after the measured acceleration, the trajectory had adjusted to intersect the gravitational boundary with the precision we discussed lastly. The change wasn't subtle or ambiguous. It was measurable, documented, and exactly calibrated to produce a specific outcome. This is where the timing becomes as important as the magnitude. If you're a comet experiencing random outgassing, the timing of that outgassing relative to your orbit is essentially arbitrary. Ice heats up when the Sun hits it, regardless of whether that happens to be gravitationally convenient. But if you're something capable of choosing when to fire thrusters, perihelion is exactly where you'd do it. You'd wait until you were deep in the Sun's gravity well, where every unit of thrust produces maximum effect on your final trajectory. You'd use the Sun's own gravity to amplify whatever propulsive force you could generate, and you'd do it when you were hidden from observation, when the very geometry of the solar system made it impossible for Earth-based telescopes to watch what was happening. The observation gap matters for another reason. We don't have continuous data on what occurred during those weeks when 3I Atlas was behind the Sun. We have before and after measurements, which allow us to calculate that acceleration happened, but we don't have real-time observation of the mechanism. This creates exactly the kind of ambiguity where natural and technological explanations can coexist without definitive resolution. If you prefer natural explanations, you can point to the gap and say we simply don't know enough about what happened. Maybe it was ordinary cometary outgassing that just happened to produce an extraordinary result. If you're considering technological explanations, you can point to the same gap and note that it provided perfect cover for a maneuver that an intelligent system would want to conduct away from observation. What we do know is that after perihelion, multiple observatories detected unusual jet activity from 3I Atlas. These weren't diffuse clouds of gas spreading evenly in all directions. They were collimated streams, directed flows that suggested some kind of structure or organization to how material was leaving the object. The existence of jets isn't unusual for comets. Many comets show jet activity as they heat up. What's unusual is the pattern and persistence of these particular jets, combined with the fact that they appeared precisely after the period when we know trajectory adjustment occurred. The correlation isn't proof of causation, but it's another data point that fits one interpretation considerably better than the other. There's also the question of energy. When you measure the brightness and extent of the jets observed coming from 3I Atlas, when you calculate how much material would need to be vaporizing to produce those visual effects, you run into a problem. The object's estimated size and surface area don't easily account for the intensity of the activity observed. It's not that the numbers are impossible under natural models. You can construct scenarios involving unusually volatile composition or concentrated ice deposits that might explain it. But each explanation requires adding another special condition, another unusual characteristic, another coincidence. At some point, the accumulation of special cases starts to feel less like explanation and more like excuse-making. The physics of trajectory adjustment are straightforward once you accept that adjustment happened. An object moving through space has momentum in a particular direction. To change that direction, you need to apply force. For a natural comet, that force comes from outgassing, vaporized ice creating thrust like a leaky balloon spinning across a room. For something with propulsion capability, that force comes from controlled release of reaction mass or energy, directed thrust that produces calculated changes in velocity. The math works the same way regardless of the mechanism. What differs is the precision of the outcome. Natural processes produce scatter. Technological processes produce targeting. What we're seeing with 3I Atlas looks overwhelmingly like targeting rather than scatter. Consider the alternative scenarios. Suppose 3I Atlas is indeed just a comet, nothing more. Suppose the perihelion passage triggered ordinary outgassing that happened to fire at the right time, in the right direction, with the right intensity to adjust the trajectory toward Jupiter's hill radius, with precision matching 1 in 26,000 odds. That's possible. Unlikely things happen. But now add everything else we know, the initial trajectory that was already remarkable in how close it would bring the object to Jupiter, the timing of the acceleration at the optimal point in the orbit for maximum efficiency, the post-perihelion jets that appeared exactly when you'd expect to see evidence of propulsion, the arrival prediction matching a gravitationally significant boundary. Each of these factors individually might be dismissible. Collectively, they form a pattern that natural explanations struggle to accommodate without resorting to an accumulation of fortunate coincidences. This is the distinction between skepticism and denialism. Skepticism says, show me the evidence, prove your case, don't ask me to believe without verification. That's healthy scientific thinking. Denialism says, I will explain away any pattern, dismiss any correlation, demand impossible standards of proof while accepting comfortable explanations with no proof at all. When multiple independent lines of evidence point toward the same conclusion, when the mathematics describe precision that mimics intentionality, when the timing and magnitude of observed changes align, exactly with what you'd expect from controlled navigation, skepticism should shift from prove it's not natural to explain how the natural scenario produces this specific outcome. The burden of proof doesn't belong exclusively to the extraordinary claim. It belongs to whichever explanation struggles most to account for what we're actually observing. The beauty of this situation is that we don't have to settle the debate through argument. March 2026 will provide data that favors one interpretation or the other. If 3I Atlas continues on its predicted course without further adjustment, if it arrives at Jupiter's hill radius exactly as calculated based on the perihelion acceleration, that's powerful evidence that whatever happened during that observation gap was precise and intentional. If the object deviates significantly, if it shows further course changes that move it away from the predicted intersection, that tells us something important about how much control might be involved. And if it arrives at the hill radius and then does something we're not anticipating, if it releases objects, if it changes velocity in ways that don't match natural explanations, if it demonstrates behavior that can't be attributed to cometary processes, then we're facing a situation that demands immediate and comprehensive investigation. For now, what we have is the clearest case yet of an interstellar object, demonstrating trajectory characteristics that look nothing like passive celestial mechanics and everything like navigation. The course correction that occurred during perihelion wasn't just measurable, it was meaningful. It changed the trajectory in exactly the way needed to achieve a specific outcome at a specific location. Whether that happened through extraordinary natural coincidence or through deliberate technological action is the question that divides reasonable people examining the same data. What shouldn't divide anyone is the recognition that this deserves serious investigation rather than comfortable dismissal. The data showing precise trajectory adjustment raised questions that demanded institutional response. In November 2025, NASA convened a briefing to present findings from 8 different missions that had observed 3I Atlas. The anticipation was significant. Would the agency acknowledge the anomalies, or would it do what institutions often do when faced with uncomfortable implications? What happened at that briefing revealed as much about how we handle the unknown as it did about the object itself. The NASA briefing in November 2025 was supposed to be a milestone moment. 8 different space missions, including observations from Mars orbiters, Earth-based telescopes, and specialized instruments designed for studying comets, had gathered data on 3I Atlas. The astronomical community was watching closely, waiting to see how NASA would frame what many researchers were privately calling one of the most anomalous objects ever tracked. Would the briefing acknowledge the mathematical precision of the Jupiter approach? Would it address the unusual acceleration patterns? Would it grapple with the accumulation of strange characteristics that were making this object impossible to categorize comfortably? The tone of the briefing when it came was methodical and reassuring. Officials presented images showing a small, faint object with the visual characteristics you'd expect from a distant comet. They discussed spectroscopic data indicating the presence of familiar cometary materials. They walked through trajectory calculations, confirming that yes, the object was heading in Jupiter's general direction, but framed it as just another example of orbital mechanics playing out across the solar system. The explicit message, delivered with the authority that comes from institutional credibility, was clear. 3I Atlas is interesting, scientifically valuable for what it can teach us about interstellar objects, but fundamentally ordinary in the grand scheme of celestial phenomena. It's a comet. Strange in some ways, but not extraordinary. The subtext was even clearer. There's nothing here that should concern or excite anyone beyond professional astronomers doing routine science. Avi Loeb's response came swiftly and publicly. He didn't couch his criticism in diplomatic language or academic hedging. He stated directly that NASA was minimizing the anomalies, presenting a sanitized version of the data that downplayed precisely the aspects that demanded explanation. His concern wasn't that NASA was lying or concealing information. The data was public, available to anyone with the technical ability to analyze it. His concern was that the framing, the emphasis, the editorial choices about what to highlight and what to gloss over were all designed to lower expectations and discourage exactly the kind of serious investigation that the situation warranted. This wasn't speculation on Loeb's part, it was pattern recognition. He'd seen it before with previous anomalous objects, this institutional instinct to normalize rather than investigate, to reassure rather than question. One specific example from the briefing illustrates the disconnect between what was shown and what it might mean. NASA presented images from the HiRISE camera aboard the Mars Reconnaissance Orbiter, one of the highest resolution imaging systems we have pointed at objects in deep space. The images showed 3I Atlas with a notable forward-facing glow, a brightness concentrated in the direction of travel rather than streaming behind the object as you'd expect from a typical comet tail. The briefing acknowledged this feature but framed it as interesting rather than anomalous. A quirk worth studying, but not something that challenged our understanding of how comets behave. Loeb looked at the same images and saw something that didn't fit cometary models at all. A forward glow suggesting material being pushed ahead of the object, possibly by some kind of directed energy or protective mechanism, rather than being left behind as the object ploughed through space. This is where the divide becomes philosophical rather than just scientific. NASA's approach represents what you might call evidential conservatism. Don't make extraordinary claims until you've exhausted every possible ordinary explanation, even if those ordinary explanations require stacking multiple unlikely factors on top of each other. Loeb's approach represents evidential proportionalism. When you see multiple indicators pointing in the same direction, when the accumulation of anomalies starts forming a pattern, investigate that pattern seriously rather than explaining away each piece individually. Both approaches have historical justification. Conservative methodology has protected science from countless false alarms and premature conclusions. Proportional methodology has enabled breakthroughs that never would have happened if researchers had waited for perfect certainty before exploring uncomfortable possibilities. The question isn't which philosophy is correct in abstract terms. The question is which approach better serves the actual situation we're facing with 3i Atlas. If this turns out to be a natural object with unusual but ultimately mundane characteristics, then NASA's conservative framing will have been vindicated, and Loeb's concern will look like overreaction. But if this turns out to be something that demands explanation beyond natural cometary processes, if March 2026 arrives, and we see behaviour that can't be dismissed with comfortable narratives, then the minimisation in that November briefing will look like a missed opportunity at best and institutional failure at worst. The stakes are asymmetric. Investigating and finding nothing wastes some resources and professional credibility. Not investigating and missing something significant wastes the chance to understand something profound about our place in the cosmos. The institutional caution isn't coming from malice or conspiracy. It's coming from a reasonable fear of being wrong in a way that damages credibility. NASA operates in a political environment where funding depends on maintaining public trust, where spectacular claims that turn out to be false can have long-lasting consequences for the agency's ability to conduct its mission. The scientific community has been burned before by premature announcements about potential biosignatures or anomalous signals that turned out to have conventional explanations. Everyone remembers the phosphine on Venus claim that fell apart under scrutiny, or the arsenic-based life announcement that couldn't be replicated, or dozens of other instances where caution would have prevented embarrassment. This institutional memory creates powerful incentives to wait, to verify, to demand ironclad evidence before making any statement that might raise expectations. But there's a difference between appropriate caution and reflexive dismissal. Appropriate caution says we need more data, better observations, systematic study before reaching conclusions. Reflexive dismissal says we already know what this is, the anomalies aren't really anomalous once you understand them properly. Anyone suggesting otherwise is being sensational. The November briefing leaned toward dismissal. It didn't call for intensive observation campaigns. It didn't highlight the need for coordinated multi-wavelength studies. It didn't frame March 2026 as a critical opportunity to gather definitive data. It framed the whole situation as interesting but routine, worthy of continued monitoring but not special attention. That framing might be accurate, or it might be the kind of comforting narrative institutions tell themselves when they're afraid of the implications of taking something seriously. Loeb's criticism matters not because he's infallible, or because his interpretation is necessarily correct, but because he's raising questions that deserve answers rather than dismissal. When you have an object displaying the kind of precision we've discussed, when the trajectory matches gravitationally significant boundaries within margins that strain coincidence, when the timing and magnitude of course corrections align with what you'd expect from intentional navigation, the response shouldn't be, it's just a comet with unusual properties. The response should be, we don't fully understand what's happening here, and we need to investigate systematically until we do. That's not sensationalism. That's the scientific method applied honestly to a situation that doesn't fit established patterns. The debate between institutional caution and investigative urgency will continue regardless of what any individual researcher or agency believes. What matters more is what happens with observation and analysis over the coming months. Will there be coordinated campaigns to study 3i Atlas with every available instrument, gathering the kind of comprehensive data that could resolve ambiguities? Or will we continue with opportunistic snapshots, fragmented observations, and explanations that require piling coincidence upon coincidence to maintain comfortable conclusions? The answer to that question will tell us as much about humanity's readiness to confront cosmic mysteries as it will about the nature of the object approaching Jupiter. To understand why this debate matters, why Loeb's criticism of NASA's framing deserves serious consideration, you need to see the full picture of what makes 3i Atlas anomalous. The trajectory precision is just one piece. When you catalogue everything unusual about this object, when you lay out all the characteristics that don't fit comfortably into natural models, the accumulation becomes harder and harder to explain away with casual reassurances. Scientific anomalies rarely announce themselves with obvious drama. They show up as small deviations from expected values, subtle patterns in data, measurements that fall just outside the range you'd consider normal. Any single anomaly can usually be explained with some combination of measurement error, unusual but natural circumstances, or incomplete understanding of the system you're observing. But when anomalies start accumulating around the same object, When multiple independent measurements all point towards something being fundamentally different from what you'd expect, that's when pattern recognition should override individual dismissals. What follows is a systematic look at the characteristics of 3i Atlas that have raised concerns among researchers willing to look carefully at the full dataset rather than focusing only on the aspects that fit comfortable models. Start with the optical properties, because this is where some of the most striking deviations appear. When light reflects off an object in space, it becomes polarized in predictable ways depending on the surface composition and texture. Dust particles, ice crystals, rocky surfaces, each produces a characteristic polarization signature that astronomers use to determine what they're looking at without needing to visit the object directly. For typical comets, you see moderate positive polarization, meaning light waves align in a particular orientation as they bounce off the dusty atmosphere surrounding the nucleus. This has been confirmed across hundreds of observed comets. It's so consistent that polarization measurements are standard tools for cometary analysis. 3i Atlas shows something completely different: extreme negative polarization, far beyond anything previously measured for a cometary object. The light coming from it is polarized in the opposite direction from what cometary dust should produce, and the magnitude of this reverse polarization exceeds anything in the observational record for objects classified as comets. This isn't a subtle difference. This isn't the polarization is a bit unusual. This is the polarization signature doesn't match the category we're placing this object in. The attempts to explain this through natural means have involved suggesting exotic dust compositions or unusual grain sizes, but none of the proposed natural explanations fully account for the magnitude of the deviation. What you'd need is material with optical properties dramatically different from ordinary cometary dust, organized in ways that produce coherent polarization effects maintained across the entire visible portion of the object. Each of those requirements is possible individually. Together, they represent a combination of special conditions that starts looking less like explanation and more like theoretical improvisation designed to preserve a preferred conclusion. The color of the object presents another puzzle. Most comets show reddish hues, consistent with organic materials and iron compounds being exposed to space radiation over millions of years. This reddening effect is so common it's considered a baseline expectation. 3. I-Atlas appears distinctly less red than typical comets, showing color properties that suggest either very different composition or very different exposure history. By itself, unusual color wouldn't be decisive evidence of anything extraordinary. Combined with the polarization anomaly, it becomes another indicator that this object's surface properties don't match the cometary template we're trying to fit it into. Move from optical properties to chemical composition, and the pattern continues. Spectroscopic analysis allows astronomers to identify elements and molecules present in an object by examining which wavelengths of light it absorbs or emits. For 3i Atlas, one of the most puzzling findings is the detection of nickel emission without corresponding iron detection. In natural cosmic environments, nickel and iron almost always occur together. They're forge mates from stellar nuclear synthesis, chemically similar elements that behave similarly under most conditions. Finding nickel without iron is like finding smoke without heat. Not impossible, but requiring special explanation. You'd need processes that specifically separate these elements or environments where one is present but the other isn't, neither of which fits comfortably with how we understand cometary formation and composition. Water content provides another point of departure from expectations. Comets are often called dirty snowballs because their composition is dominated by water ice, mixed with dust and rocky material. When comets approach the sun and heat up, water vapor is typically the primary component of the outgassing that creates their characteristic tails and comas. Multiple observations of 3i Atlas have shown surprisingly low water signatures relative to the level of activity the object displays. The gas emissions and visible features suggest substantial outgassing is occurring, but the spectroscopic signatures don't show the amount of water vapor you'd expect from that level of activity. Either the object has unusually low water content for a comet, or the activity we're seeing is being produced by something other than water vaporization. Both possibilities are strange. Neither fits smoothly into standard cometary models. The behavior of the jets themselves deserves careful attention. When comets outgas, the resulting jets are typically influenced by the object's rotation. As the comet spins, active areas on its surface rotate in and out of sunlight, creating jets that appear and disappear, change direction, vary in intensity according to rotational period. It's predictable and well documented across countless observations. The jets observed from 3i Atlas show less correlation with rotation than you'd expect. They appear more stable, more consistently directed, less affected by the tumbling motion that should be constantly changing which parts of the surface face the Sun. This suggests either that the active regions are distributed in an unusually symmetrical way that compensates for rotation, or that the jets are being produced by mechanisms not entirely dependent on solar heating of surface ice. Again, you can construct natural scenarios that might explain this. Perhaps the object has active vents distributed evenly across its surface. Perhaps its rotation axis is aligned in an unusual way relative to its orbit. But each explanation requires adding another special condition to the growing list of ways this object happens to be different from the patterns we see everywhere else. Thermal observations add another layer of strangeness. When you measure the infrared emission from a comet, you're detecting heat radiated from its surface after absorbing sunlight. The temperature distribution and intensity tell you about surface composition, how efficiently the material absorbs and re-radiates energy, how much surface area is exposed to sunlight. For 3i Atlas, the thermal profile doesn't quite match what you'd predict from its visible brightness and estimated size. The object appears either smaller than visual observations suggest with unusually high thermal efficiency, or larger than calculated with surface properties that don't match typical cometary materials. The ambiguity itself is telling. We're having trouble making consistent sense of measurements that should fit together straightforwardly if this were an ordinary comet. The trajectory itself, even before considering the hill radius precision, shows unusual characteristics. Interstellar objects entering our solar system should follow hyperbolic paths, trajectories that swing through once and never return, following the geometry determined by their initial velocity and the Sun's gravity. 3i Atlas is on such a hyperbolic trajectory, but its specific path shows elements that raised eyebrows even before the hill radius alignment became clear. The inclination and orientation of its orbit aren't random, but rather aligned in ways that brought it through the inner solar system at times, and locations that maximized observation opportunities while also positioning it for close planetary encounters. You can attribute this to chance. The universe is large, rare trajectories happen, but it's another entry in the catalogue of ways this object seems remarkably well positioned for what's unfolding. The object's brightness changes present another puzzle. Most comets show predictable patterns of brightness variation as they rotate, with brighter and darker regions coming into view at different times. The rotation period can usually be determined by analysing these brightness fluctuations. For 3i Atlas, the brightness variations don't show the clear periodicity you'd expect from a simple rotating body. The changes seem more erratic or complex, suggesting either an unusually irregular shape, complex rotation involving tumbling on multiple axes, or surface properties that vary in ways not typical of cometary nuclei. Complex rotation is possible for natural objects, especially if they have undergone collisions or fragmentation. But combined with everything else, it becomes another characteristic that doesn't quite fit the simplest natural model. There's also the curious alignment with the direction of the WOW signal, that famous potential SETI detection from 1977 that has never been satisfactorily explained or repeated. The trajectory of 3i Atlas, when traced back to its origin direction, comes from a region of sky that includes the location where the WOW signal appeared to originate. This is almost certainly coincidence. The WOW signal was a radio burst lasting 72 seconds, never confirmed, with no established connection to any specific star or object. But for those keeping a comprehensive catalogue of curious facts about 3i Atlas, the directional alignment adds one more entry to the list of things that make you pause and wonder. The timing of the object's arrival, while not anomalous in itself, becomes interesting when you consider the broader context. 3. The Atlas is approaching Jupiter during a period when we have unprecedented observational capabilities in place. Multiple missions at Mars, advanced Earth-based telescopes, space observatories covering multiple wavelengths, and instruments specifically designed to study comets and asteroids. If you were planning a mission to study our solar system and wanted to be observed during your approach to Jupiter, arriving now would maximize the chances of detection and characterization. This is the weakest point in the entire catalogue, easily dismissed as observation bias. We detect more things now because we're looking harder with better tools. But it contributes to the overall pattern of an object that seems almost designed to be noticed and tracked. The apparent density of the object, inferred from its brightness and behaviour, doesn't match typical cometary densities cleanly. Comets are usually porous, loosely bound collections of ice and dust with densities well below solid rock. The way 3i Atlas responds to non-gravitational forces, the relationship between its brightness and estimated size, these suggest either higher density than typical comets or an unusual shape that affects how we interpret the observations. Higher density would mean either different composition, more rock than ice, or some degree of internal structure. Different composition doesn't fit well with the observed activity and outgassing. Internal structure doesn't fit with how we think comets form and evolve. Either way, another characteristic that pulls away from the standard template. The object shows what appears to be accelerated evolution of its activity. Early observations showed minimal cometary features, no obvious tail or coma, just a point source like a distant asteroid. As it approached the Sun, activity increased, but faster than models predicted based on typical cometary warming curves. The rapid onset of jets and gas emission suggests either the object has unusually volatile material very close to its surface, or the activity is being triggered by mechanisms that respond to solar heating differently than water ice sublimation. This could indicate exotic composition, materials that vaporize at lower temperatures than water, or it could indicate internal heat sources complementing solar warming. Natural radioactive decay can provide internal heating, but usually not at levels that would dramatically affect cometary activity at the distances we're discussing. Then there's the broader statistical context. We've now detected a handful of confirmed interstellar objects passing through our solar system. Each has shown unusual characteristics. Oumuamua with its extreme elongation and unexpected acceleration. Borisov with its surprisingly ordinary appearance despite coming from interstellar space, and now 3i Atlas with its catalogue of anomalies. The small sample size makes statistical statements dangerous, but it's worth noting that we're not seeing a clear population of typical interstellar comets. We're seeing objects that each challenge our expectations in different ways. Either our models of what to expect are badly wrong, or the population of interstellar visitors is more diverse than we imagined, or we're detecting a non-random sample that includes objects with characteristics making them more observable or more interesting. Each explanation has implications. Taking all of this together, the optical anomalies, the chemical peculiarities, the behavioral oddities, the trajectory precision, the timing, the density questions, you face a choice in how to interpret the pattern. One interpretation says we're seeing an unusual but natural object, a comet with properties at the extreme end of natural variation, experiencing a series of coincidences that happen to align in ways that superficially suggest intentionality. The natural explanation requires assuming that multiple independent characteristics, each of which would be unusual on its own, happen to combine in a single object that also happens to be on a trajectory targeting Jupiter's Hill radius, with extraordinary precision. The alternative interpretation says we're seeing an object whose properties don't fit the natural template because it isn't entirely natural, because some or all of its characteristics reflect design rather than cosmic accident. Neither interpretation is proven. Both require accepting things that seem unlikely. The natural explanation requires accepting an improbable convergence of unusual characteristics. The technological explanation requires accepting that something built by intelligence is moving through our solar system. The question isn't which explanation feels more comfortable. The question is which explanation requires fewer special assumptions, fewer just-so stories, fewer coincidences stacked on coincidences. The natural explanation gets more complicated with each new anomaly. The technological explanation remains simple. If you assume capability for interstellar travel and interest in Jupiter, everything else follows logically from mission planning principles we understand from our own space exploration efforts. This catalogue isn't complete. New observations continue generating new data. And some of what we currently think we know will be refined or corrected as measurement precision improves. But the pattern is established and growing stronger rather than weaker. The more we look at 3i Atlas, the more it resists fitting into the comfortable categories we'd like to place it in. That resistance to categorization is itself meaningful. It's a signal that something about our understanding is incomplete, whether that incompleteness is in our models of natural cometary behavior, or in our assumptions about what moves through interstellar space. If the catalogue of anomalies suggests that natural explanations are straining under the weight of accumulated coincidences, then what would a technological explanation actually look like in practice? What specific capabilities would be involved? What mechanisms would produce the observed characteristics? And why would something with those capabilities be interested in Jupiter's gravitational boundary? Let's be precise about what we're discussing when we talk about a technological interpretation of 3i Atlas. This isn't about little green men or science fiction fantasies. This is about asking what characteristics we'd expect to see if an object were demonstrating controlled interstellar navigation, and then comparing those expected characteristics against what we're actually observing. The match isn't perfect. Nothing about this situation offers certainty, but the alignment between prediction and observation is striking enough that dismissing the possibility without serious investigation starts looking less like scientific caution and more like ideological commitment to a preferred answer. Start with the propulsion question. If 3i Atlas were capable of adjusting its trajectory, what would that look like to our telescopes? You wouldn't expect to see massive rocket plumes or glowing engines like in Hollywood depictions. At the distances and scales we're discussing, even significant thrust would appear as subtle effects, changes in velocity not fully explained by gravity, jets of material being expelled from the object, gradual adjustments to the trajectory that accumulate over time. This is exactly what we observe. The non-gravitational acceleration detected during perihelion, the collimated jets appearing after that acceleration, the resulting trajectory change that produces the hill radius intersection, all of this matches what you'd predict from a propulsion system operating at the threshold of our detection capabilities. The jets themselves deserve closer examination through this lens. If you were designing a propulsion system for an interstellar probe, you'd want something efficient and controllable. You wouldn't waste reaction mass on continuous thrust, when most of your journey involves coasting through empty space. You'd make trajectory adjustments at gravitationally significant points where the Oberth effect multiplies your propulsive efficiency, exactly what we see happening at perihelion. The jets observed from 3i Atlas show characteristics more consistent with directional thrust than with random outgassing. They're stable, persistent, less affected by rotation than natural cometary jets should be. If these are thrusters rather than natural ice vaporization, the behavior matches engineering logic perfectly. The perihelion timing becomes especially significant under the technological hypothesis. If you're approaching a solar system from interstellar space, and you want to position yourself relative to Jupiter, you have limited opportunities to make large trajectory adjustments efficiently. You could fire your thrusters continuously, but that wastes reaction mass and increases the risk of detection. Or you could wait until you're deep in the sun's gravity well, where every unit of thrust produces maximum change to your final trajectory, and where the sun itself blocks observation from the inner planets. This is exactly what happened. The course correction occurred at perihelion, hidden from Earth-based observation, at the optimal point in the orbit for efficient maneuvering. Either that's extraordinary coincidence, or it's mission planning. The forward-facing glow that NASA's HiRISE camera detected raises another possibility. If you're traveling through interstellar space at high velocity, even tiny dust particles become dangerous projectiles. The relative velocity turns microscopic grains into high energy, impacts that could damage sensitive equipment, or erode protective shielding over the vast distances involved in interstellar travel. One proposed solution to this problem involves projecting a beam of energy ahead of your spacecraft, a laser or particle beam that vaporizes or deflects incoming particles before they can impact your hull. From a distance, this would appear as a glow in the direction of travel, exactly what the HiRISE images show. Natural comets don't produce forward glows, their material streams behind them, but a spacecraft using a micrometeoroid defense system would show exactly this signature. Now consider why Jupiter's hill radius matters as a destination. If you're conducting a mission to study our solar system, why target Jupiter? Earth would seem like the obvious choice if your interest is in finding or studying life, but Earth is also the most actively monitored planet in our system, surrounded by satellites, tracked by ground-based radars, watched constantly by millions of observers. Approaching Earth without detection would be nearly impossible. Jupiter offers different strategic advantages. It's massive enough to have a substantial hill radius, a gravitational sphere where you could position objects with some stability. Its Lagrange points provide locations where something could remain relatively stationary with minimal propulsive effort. Its moons are geologically active, chemically diverse, potential harbours for life, or at least complex chemistry. And its position in the outer solar system means less intensive observation than the inner planets receive. If the goal were to deploy observational devices or leave equipment for future retrieval, Jupiter's Hill radius would be logical choice. Place something at a Lagrange point relative to Jupiter, and it remains accessible but not immediately obvious to casual observation. The devices could monitor the inner solar system from a distance, communicate with other mission elements, or simply wait in stable positions for later phases of whatever operation they're supporting. This isn't wild speculation. It's how we design our own space missions. When we want to study a planetary system, we use gravitational anchors and stable orbits to position our instruments efficiently. Assuming a technological civilization would use similar principles isn't anthropocentric bias. It's recognition that orbital mechanics and energy efficiency don't change based on who's doing the calculating. Detection of such devices is theoretically possible but practically difficult. The Juno spacecraft, currently orbiting Jupiter, has instruments capable of detecting objects near the planet if they're large enough and reflective enough. If 3i Atlas deploys something as it passes through the Hill radius, and if that something is sizable, and if Juno happens to be looking in the right direction, we might see it. But space is vast even in planetary neighbourhoods, and finding something that doesn't want to be found, especially if it's designed with stealth considerations, would be extraordinarily challenging. This doesn't mean we shouldn't look. It means we should look systematically, with realistic expectations about how difficult the search might be. The technological hypothesis also provides coherent explanation for many of the catalogue anomalies we discussed earlier. The unusual polarization makes sense if the surface isn't primarily natural dust, but includes engineered materials with specific optical properties. The nickel without iron signature could indicate artificial alloys, or selective use of elements based on engineering requirements rather than cosmic abundance. The low water content fits if the object isn't primarily a natural comet, but rather a spacecraft using ice as radiation shielding or reaction mass, with most of its structure being something else entirely. The stable jets align with directional thrusters. The thermal anomalies could reflect internal power sources. The rapid onset of activity might indicate powered systems activating rather than passive response to solar heating. This doesn't mean every anomaly points definitively toward technology. It means the technological hypothesis offers explanatory coherence, a single framework that accounts for multiple observations without requiring separate special pleading for each anomaly. Natural explanations can account for each individual oddity if you're willing to stack enough unusual but possible conditions. The technological explanation accounts for them collectively as natural consequences of purpose-built systems doing what they were designed to do. The counter-argument is always ready. Extraordinary claims require extraordinary evidence, and we don't have proof of technology. This is true. We don't have images showing artificial structures. We don't have spectroscopic signatures of industrial processes. We don't have intercepted communications or detected power sources. What we have is behavior that matches what we'd predict from controlled navigation, combined with characteristics that strain natural explanation but fit technological interpretation comfortably. The threshold for extraordinary evidence is subjective. At what point does accumulated indirect evidence become compelling enough to justify investigation that takes the possibility seriously? Consider what proof would actually look like if 3i Atlas were technological. Unless it does something completely unambiguous, unless it suddenly changes course in ways that violate conservation of momentum, or starts broadcasting radio signals or deploys visibly artificial objects, we'll always have wiggle room for natural explanations. You can construct theoretical scenarios where unusual natural processes mimic technological signatures. The universe is strange enough that almost anything is possible somewhere. But possibility isn't probability. When you have to invoke increasingly complex natural mechanisms to avoid a simple technological explanation, when each new observation requires adding another special condition to your natural model while fitting seamlessly into the technological model, the evidential balance shifts whether we're comfortable admitting it or not. The philosophical question underneath all of this is whether we're even ready to recognize technological artifacts if they're present. We've spent decades searching for radio signals from distant civilizations, building our SETI programs around the assumption that we'd recognize intelligence by its communications. But what if intelligence visits rather than broadcasts? What if the artifacts are physical rather than electromagnetic? What if we're looking at one right now and arguing about whether comets can do strange things instead of asking whether the strange things we're seeing are actually cometry? Our detection strategies are biased towards specific assumptions about how other civilizations would behave, what technologies they'd use, how they'd make themselves known. An approach that prioritizes stealth over announcement, observation over contact, physical presence over remote communication would be harder to detect and easier to explain away. This doesn't mean we should abandon skepticism or accept every anomaly as evidence of aliens. It means we should calibrate our skepticism appropriately to the actual situation. When you have one anomaly, skepticism is cheap and appropriate. When you have multiple independent anomalies clustering around the same object, when you have trajectory precision matching 1 in 26,000 odds, when you have timing and efficiency suggesting optimization rather than randomness, skepticism should evolve into investigation. The technological hypothesis isn't proven, but it's credible enough, supported by enough indirect evidence, coherent enough in its explanatory power, that dismissing it without systematic investigation starts looking like ideological resistance rather than scientific rigor. March 2026 approaches. If 3i Atlas continues to its predicted rendezvous with Jupiter's Hill radius, if it arrives with a precision that current calculations suggest, we face a choice. We can continue explaining away each observation with increasingly elaborate natural mechanisms, or we can acknowledge that the simplest explanation, that something capable of navigation is navigating, deserves serious consideration. The data won't force anyone to accept the technological hypothesis, but it will make the natural alternative harder and harder to maintain without intellectual contortions that reveal more about our psychological need for comfortable answers than about what's actually happening in our solar system. Even with everything we've discussed, there's a massive caveat that intellectual honesty requires us to address. The data we have on 3i Atlas, while intriguing, is fragmentary. Our observations have been opportunistic rather than systematic, scattered across different instruments using different methods, creating exactly the kind of information gaps where both natural and technological interpretations can hide, without definitive resolution. Here's what scientific humility looks like when applied honestly to this situation. We don't know enough. The observations of 3i Atlas that have generated all this analysis and debate are not the product of a coordinated, comprehensive study designed to characterize every aspect of the object with systematic rigor. They're snapshots, different telescopes catching glimpses when the object happened to be observable from their locations, using whatever instruments and methods were available at the time, generating data points scattered across weeks and months rather than continuous coverage that would show us exactly what's happening. This fragmentation creates ambiguity that cuts both ways. It leaves room for natural explanations to hide in the gaps, and it leaves room for technological interpretations to explain the gaps as deliberate timing. The polarization measurements, as striking as they are, come from limited observation windows using instruments that weren't specifically designed to study interstellar objects with potential anomalous properties. We have data points showing extreme negative polarization at certain times, from certain angles, under certain lighting conditions. What we don't have is continuous polarization mapping across the object's rotation, across its orbital positions, across multiple wavelengths simultaneously. This means we can't rule out that what we're seeing is an unusual but natural effect of specific geometric configurations, even though the magnitude of the deviation from typical cometry values remains extraordinary. The chemical composition data faces similar limitations. Spectroscopy is powerful but requires clear observation conditions, sufficient light from the object, and careful calibration to distinguish true signals from noise and atmospheric effects. The nickel detection without iron is based on specific spectral lines observed during specific windows. The low water signature comes from measurements taken when the object was at certain distances from the Sun. We don't have comprehensive chemical mapping that would show us exactly what's present, in what proportions, how it varies across the surface, how it changes with time. This doesn't invalidate the observations we have. The data is real and properly collected using established methods. But it means our picture is incomplete enough that alternative explanations for any specific measurement can't be definitively ruled out. The trajectory measurements are the most robust part of our dataset because they're based on positional observations across many months from many facilities. When hundreds of observatories contribute data points showing where the object was at specific times, the accumulated precision becomes substantial. But even here, there are gaps. The perihelion passage behind the Sun represents weeks when we couldn't observe the object directly. We infer what happened during that time from before and after measurements, calculating that acceleration occurred and measuring its effects on the subsequent trajectory. But we didn't watch it happen in real time. We don't have detailed observations of how the jets evolved during perihelion, what their intensity profiles looked like, how their direction changed. This gap is where the ambiguity lives. Natural outgassing could have produced the measured effects, or controlled thrust could have, and the observation window that would distinguish between these possibilities didn't exist. What would proper systematic study look like? It would start with dedicated observation time on multiple facilities, providing continuous or near-continuous coverage. You'd want optical telescopes characterizing brightness and color changes at high temporal resolution. You'd want infrared observatories measuring thermal emission to build detailed temperature maps. You'd want spectroscopy across multiple wavelengths simultaneously, not scattered observations when the object happens to be visible. You'd want radar observations if the object comes close enough, providing direct measurement of shape, rotation, and surface properties that spectroscopy and imaging can't match. You'd want coordination between ground-based facilities and space telescopes to ensure no critical observation windows are missed. The James Webb Space Telescope represents an extraordinary opportunity that hasn't been fully utilized. Webb sensitivity in the infrared could detect thermal emissions that reveal internal heat sources or unusual cooling patterns. Its spectroscopic capabilities could map chemical composition with unprecedented detail. Its position at the L2 Lagrange point provides observation geometry that ground-based telescopes can't achieve. But telescope time is precious. Proposals compete against hundreds of other worthy scientific objectives, and securing the hours needed for comprehensive study of 3i Atlas requires convincing scheduling committees that the target justifies the investment. So far, that comprehensive study hasn't happened. We've gotten scattered observations when other projects had a bit of spare time or when specific researchers advocated strongly enough to get limited windows. The result is that we're trying to solve a complex puzzle with pieces missing. Each interpretation, natural or technological, can point to the gaps and say, we need more data before concluding anything definitively. This is scientifically honest, but it also risks becoming an excuse for not taking the situation seriously enough. When you have multiple independent indicators all pointing in directions that challenge comfortable assumptions, waiting for perfect data before investigating seriously isn't caution, it's avoidance. The investigation should be happening now, not because we've proven something extraordinary, but because the accumulated evidence justifies treating this as a priority target, deserving systematic attention. There's also the question of what we're not looking for because we don't expect to find it. Observation strategies are designed around assumptions about what's worth measuring. If you're convinced you're looking at a comet, you measure the things that matter for comets: water content, dust composition, rotational period. You might not look for low-frequency radio emissions that could indicate electrical activity. You might not search for periodic signals that could indicate active systems operating on regular cycles. You might not analyze the jets for collimation properties that would distinguish directed thrust from isotropic outgassing. The gaps in our knowledge aren't just about where we haven't looked. They're about what we haven't looked for, the measurements we didn't think to make because they seemed irrelevant given our categorical assumptions. This is where Loeb's criticism of NASA's approach becomes most pointed. It's not that NASA is hiding data or refusing to observe, it's that the observation strategy has been guided by the assumption that comprehensive characterization isn't necessary because we already know the category this object fits into. If you've decided it's a comet, then unusual features are just variations on cometary behavior. Worth noting, but not worth the kind of intensive study you'd devote to something genuinely mysterious. But if the unusual features are potentially indicators of something beyond cometary processes, then the observation strategy should be completely different. More systematic, more comprehensive, more urgent given the time-limited opportunity we have before the object moves beyond easy observation. The practical consequence of these gaps is that March 2026 will arrive without us having the data quality we should have had. We'll observe whether 3i Atlas reaches Jupiter's Hill radius as predicted. We'll see whether it does anything obviously anomalous at that point. But we won't have the kind of detailed characterization that would let us distinguish definitively between complex natural behavior and simple technological function. We'll be in the same position we're in now, looking at suggestive but not conclusive evidence, arguing about interpretation, able to construct explanations for either possibility, but unable to prove either one. This outcome isn't inevitable. The window hasn't closed yet. Between now and March 2026, there's time for the kind of coordinated observation campaign that could fill the critical gaps. What's needed is institutional will to treat this as a priority, rather than just another interesting object in a sky full of interesting objects. What's needed is recognition that the accumulation of anomalies, even if each is individually deniable, collectively justifies investigation that matches the potential significance of what we might be witnessing. What's needed is willingness to take the technological possibility seriously enough to look for evidence that would distinguish it from natural alternatives, rather than assuming natural alternatives and only measuring things that fit that assumption. The gaps in our knowledge are real and substantial. They create legitimate uncertainty about what 3i Atlas actually is and what its arrival at Jupiter's Hill radius will mean. But acknowledging gaps shouldn't become an excuse for not trying to fill them. The time to say we need more data is before the object becomes too distant to study effectively, not after we've missed the opportunity and are left with the same ambiguity we could have resolved with appropriate effort. This is the essence of what Loeb is advocating, not certainty about what 3i Atlas is, but urgency about studying it while we can, with the thoroughness that the situation justifies. We've examined the precision, the anomalies, the hypothesis, and the gaps. Now the question becomes not just what we know or don't know about 3i Atlas, but what we choose to do about the situation we're in. Whether this object is natural or technological, whether it represents extraordinary coincidence or extraordinary intention, the story we're living through right now is already significant. How we respond to it says as much about us as any answer about the object itself will. Let's talk about what's actually at stake here, because the implications reach far beyond one object approaching one planet in our solar system. If 3i Atlas turns out to be entirely natural, an unusual comet whose properties strain our current understanding, but ultimately fit within the boundaries of what cosmic processes can produce, that's still profoundly significant. It means interstellar space contains diversity we haven't adequately characterized. It means our models of cometary behavior need expansion to accommodate phenomena we didn't predict. It means objects from beyond our solar system can arrive with characteristics that challenge expert interpretation, forcing us to acknowledge how much we still don't understand about the universe we inhabit. There's no shame in that outcome. Science advances by encountering the unexpected and revising theories to match reality. But if 3i Atlas turns out to be something other than natural, if the technological hypothesis proves correct or even partially correct, then we're facing something civilization-altering. Not in the sense of immediate crisis or contact scenario, but in the fundamental sense of knowing we're not alone, knowing that intelligence exists beyond Earth, knowing that the universe contains others who build, who explore, who move through space with purpose and capability. This wouldn't just be a scientific discovery, it would be a philosophical watershed, a moment when humanity's self-conception shifts permanently. Every question about our place in the cosmos, every speculation about whether life and intelligence are rare or common, every debate about the significance of human civilization, all of it gets reframed by the knowledge that we're not the only ones here. The middle ground, where we never achieve certainty about what 3i Atlas is, where natural and technological explanations remain viable indefinitely, because we didn't gather the data we needed when we had the chance, that's perhaps the most frustrating possibility. It means living with permanent ambiguity about something that should have been resolvable. It means future generations looking back and asking why we didn't do more when we had the opportunity. It means letting what could be one of history's most significant moments slip through our fingers because institutional caution and fragmented observation strategies prevented the kind of systematic investigation that the situation warranted. Einstein once said that before we blame the universe for not matching our expectations, we should check whether our expectations were reasonable in the first place. The sentiment applies perfectly here. We've built models of what to expect from comets based on observing objects from our own solar system, formed under conditions specific to our Sun's neighbourhood. We're extending those models to objects from interstellar space as if composition and behaviour would necessarily be identical. When an interstellar object shows up not matching the template, we face a choice: force it into the category anyway by explaining away each deviation, or admit that our expectations might have been too narrow. This isn't about abandoning scientific models. It's about recognizing when accumulated deviations suggest the model itself needs revision rather than the data needing reinterpretation. The path forward from here requires something we're often reluctant to embrace: genuine open-mindedness that doesn't prejudge the answer, but follows evidence wherever it actually leads. That means not assuming this must be natural because technological explanations feel uncomfortable. It also means not assuming this must be technological because that would be exciting. It means looking at what we observe, testing different explanations against that evidence, and assigning probability based on which explanation requires fewer assumptions and better fits the full dataset. Right now, honest application of that standard leaves both possibilities in play, with the technological hypothesis gaining weight from the precision and anomaly accumulation, while the natural hypothesis retains viability through our incomplete data and the general principle that extraordinary claims demand extraordinary evidence. What happens in March 2026 matters enormously. If 3i Atlas reaches Jupiter's Hill radius exactly as predicted, arriving at that gravitationally significant boundary with the precision that current calculations suggest, that's a result requiring explanation regardless of philosophical preferences. If it arrives and does something obviously anomalous, releases objects, demonstrates additional propulsive capability, changes course in ways that definitively rule out natural explanations, then we're past the point of debate. But even if it simply arrives as predicted and then continues onward, never doing anything unambiguously technological, the precision of that arrival within such tight margins remains evidence demanding interpretation. A 1 in 26,000 coincidence happened to produce an outcome that looks exactly like targeting. Science doesn't advance by shrugging at such coincidences. The role of observation between now and then becomes critical. Every additional data point we gather makes the eventual interpretation more robust. Every measurement we fail to make leaves ambiguity that could have been resolved. The question isn't whether we'll watch what happens in March 2026. People will definitely pay attention to that. The question is whether we'll study the object systematically in the months leading up to that moment, gathering the kind of comprehensive characterization that would let us distinguish between hypotheses with confidence. The answer depends on whether institutions allocate resources, whether researchers coordinate efforts, whether the scientific establishment decides this deserves priority attention. For those of us not operating research telescopes or planning space missions, the role is different but not insignificant. Public attention matters because it influences institutional priorities. When people care about something, when they ask questions and demand answers, when they make clear that scientific curiosity about this situation is widespread and genuine, it creates pressure for appropriate investigation. This isn't about organizing mass movements or demanding specific conclusions. It's about maintaining interest, staying informed, engaging with the actual evidence rather than just sensational headlines. It's about being part of a community that values real inquiry over comfortable narratives. Share this kind of analysis. Bring it to people who think carefully about evidence and interpretation. Discuss it with those who understand that genuine mystery is more valuable than premature certainty. Comment with your own assessment of the evidence, not what you hope is true, but what you think the data actually supports. Subscribe to channels and sources that prioritize substance over clickbait, that are willing to say, "we don't know," when appropriate, but also willing to ask uncomfortable questions when evidence justifies them. Turn on notifications for updates because this story will continue unfolding, and what we learn between now and March 2026 might shift the interpretation significantly in one direction or the other. The broader significance of this situation transcends 3i Atlas itself. How we handle this, how we investigate, how we interpret, how we communicate about it, sets precedent for how we'll approach future encounters with the unexpected. If we do this well, if we study systematically and think carefully and follow evidence honestly, we demonstrate that humanity is ready to confront genuine cosmic mysteries with maturity and rigor. If we do it poorly, if we dismiss anomalies reflexively or sensationalize them irresponsibly, If we let ideological commitments override careful analysis, then we prove we're not yet ready for the universe's complexities. Either way, what's happening now is practice for situations we'll inevitably face as our observational capabilities improve and we encounter more objects that don't fit comfortable categories. There's something profound about living through a moment when answers are still pending, when we exist in the space between question and resolution. March 2026 will come. We'll see whether predictions hold or fail. We'll gather new data that moves us closer to understanding what 3i Atlas actually is. But right now, in this moment, we have something different, genuine uncertainty about something that could be profoundly important. That uncertainty isn't weakness. It's reality acknowledging that some questions don't have easy answers, some situations require patience and careful study, some mysteries deserve investigation rather than premature conclusions. So here's what I'm asking from you. Stay curious but skeptical. Demand evidence but remain open to what that evidence suggests, even when the suggestions are uncomfortable. Don't accept either extreme, neither the reflexive dismissal that says this can't possibly be technological, nor the uncritical acceptance that says it must be. Look at the numbers, consider the probabilities, think about what accumulation of anomalies means for how we weight different explanations, and recognize that whatever the truth turns out to be, we're living through a moment where humanity is grappling with something at the edge of our understanding, something that won't be resolved by comfortable narratives or wishful thinking, but only by honest investigation and careful thought. Keep your eyes on the sky and your minds open to possibilities that our models might not have adequately prepared us for. Let's treat the next several months not as time to kill before we get answers, but as opportunity to gather the data that will make those answers meaningful when they arrive. And let's approach March 2026 not with predetermined conclusions, but with the kind of genuine curiosity that represents science at its best, ready to be surprised, willing to learn, committed to following evidence wherever it leads. The universe doesn't care what we prefer to be true. It simply is what it is. Our job is to figure out what that is, as accurately and honestly as we can manage. 3i Atlas is giving us a chance to do exactly that. Let's not waste it.